What if I told you the very first atoms in the universe weren't what we thought? For centuries, we've looked up at the night sky and wondered how it all began. The stars, the galaxies, the very fabric of reality itself. But hidden within that cosmic dawn lies one of the greatest scientific mysteries of all time: how the universe's first light elements came into existence. These primordial building blocks, hydrogen, helium, and a trace of lithium, are more than just entries on the periodic table. They are the silent witnesses to the birth of everything, the ancient fingerprints of creation itself. And what's truly astonishing is that despite decades of research, physicists and astronomers are still fiercely debating how they actually formed. It's a question that goes straight to the heart of our existence. Every atom in your body, every star in the sky, every galaxy spinning in the deep dark, it all traces back to those first few moments after the Big Bang. We used to think we had it all figured out, a straightforward story of cosmic expansion and cooling that left behind simple elements. But as our telescopes grew more powerful and our simulations more sophisticated, that neat narrative began to unravel. Strange inconsistencies emerged, unexplained abundances, observations that simply didn't match the predictions. And that's when the real wonder began, because when the answers don't come easy, the human mind does what it does best. It imagines, it theorizes, it dares to rethink reality. In this video, we're going to explore 30 of the most incredible, mind-bending theories scientists have put forward to explain the formation of the universe's first light elements. From cosmic inflation and quantum fluctuations to multiverse hypotheses and even wilder ideas that challenge our very understanding of physics, we're about to embark on a journey to the edge of human knowledge. This isn't just a story about atoms, it's a story about curiosity, about our endless drive to understand where we came from and why the cosmos is the way it is. So join me as we dive into one of the most profound mysteries of all: how the universe wrote its first chapter and why we're still deciphering its words today. Our journey begins with the most established and widely accepted explanation, the one you'll find in every textbook: Big Bang Nucleosynthesis. Picture the universe not even a second old, an unimaginably hot and dense soup of fundamental particles. For the first few minutes, it was far too energetic for anything stable to form. But then, expansion did its magic. As the cosmos rapidly grew and cooled, it reached a critical temperature, still billions of degrees, mind you, where protons and neutrons could finally start to stick together instead of being instantly torn apart. This was the universe's first and most prolific nuclear fusion reactor, operating under the most extreme conditions imaginable. It all happened in a breathtakingly short window, from about 100 seconds to just 20 minutes after the initial singularity. During this frantic period, free neutrons, which are unstable on their own, began a desperate race to find partners before they decayed. They slammed into protons to form deuterium, a heavy isotope of hydrogen. This deuterium didn't last long. It was quickly fused into helium-4, the most stable light nucleus. The entire process was a delicate dance governed by the universe's expansion rate and the fundamental forces of nature. What's truly remarkable about this theory is its stunning predictive power. By plugging in the known laws of physics and the conditions of the early universe, scientists can calculate with incredible precision how much of each element should have been forged in that cosmic pressure cooker. The math predicts that about 75% of the ordinary matter by mass should have ended up as hydrogen, and about 25% as helium-4, with only trace amounts less than a billionth of the total of deuterium, helium-3, and lithium-7. And here's the part that still leaves physicists in awe. When we look out at the oldest, most pristine corners of the cosmos, at ancient gas clouds that have never been inside a star, those predicted ratios are almost exactly what we observe. This incredible agreement between prediction and observation is a huge part of why the Big Bang theory itself is so robust. It's a foundational pillar of modern cosmology. But that word almost is doing a lot of work, because while the predictions are overwhelmingly correct, there are tiny, persistent discrepancies, particularly with that trace element lithium, that suggest the story might not be entirely complete. These tiny anomalies are the cracks where the light gets in, prompting scientists to ask if there's more to the tale. But what if that near-perfect agreement is hiding a deeper, more complex reality? This brings us to our second and truly revolutionary theory, inhomogeneous Big Bang nucleosynthesis. The standard model is built on a critical assumption that the infant universe was an almost perfectly smooth, uniform soup of matter and energy. It's a beautifully simple starting point, but what if that assumption is wrong? What if, instead of a homogeneous blend, the cosmos was born with lumps and bumps, with regions of higher and lower density right from the very beginning? Inhomogeneous Big Bang nucleosynthesis dares to challenge that foundational smoothness. It proposes that the universe's earliest moments were marked by significant fluctuations in density and temperature. Imagine a pot of water just as it begins to boil, with bubbles of vapor forming and rising in some areas while cooler, denser water sinks in others. Now magnify that turbulence to a cosmic scale in an environment of almost unimaginable energy. In this chaotic and uneven environment, the process of forging the first elements wouldn't have been a single, uniform event. It would have been a patchwork. Different pockets of the universe would have experienced nucleosynthesis under wildly different conditions. In an extremely dense region, nuclear reactions would have proceeded much faster and more efficiently, potentially creating a higher local abundance of helium. Conversely, in a lower density zone, the process might have been slower and less complete, leaving behind more unprocessed deuterium or even free neutrons. This theory turns the entire narrative from a single, cosmic-wide recipe into a grand mosaic of miniature, unique forges, each operating under its own specific set of rules. The implications for solving those persistent observational puzzles are profound. The infamous lithium problem, where the observed amount of lithium-7 in ancient stars is about 3 times lower than the standard model predicts, could potentially be explained if these inhomogeneities somehow suppressed its production or enhanced its destruction in certain areas. Similarly, slight variations in the measured deuterium abundance from one ancient gas cloud to another, which are often dismissed as measurement errors, could instead be genuine cosmic fossils relics from different density pockets that never fully mixed. This idea gains even more credibility when we consider what we now know about the universe's structure. Our cosmos today is anything but smooth. It's a vast web of galaxies, clusters, and immense voids. This large-scale structure had to come from somewhere, and cosmologists believe it grew from tiny quantum density fluctuations that were stretched to enormous sizes during a period of rapid inflation just after the Big Bang. Inhomogeneous nucleosynthesis simply suggests that some of these fluctuations were already significant enough during those first 20 minutes to leave a tangible imprint on the chemistry of the universe. It's a theory that elegantly connects the universe's first moments with its present-day structure, suggesting that the seeds of galaxies were sown even before the first atoms were fully formed. But to truly rewind the clock even further, we have to venture into a realm even more extreme than the first few minutes. We have to go back to the universe's very first microsecond, a time so incomprehensibly hot and dense that the very concepts of protons and neutrons didn't even exist yet. This brings us to our third and perhaps most exotic theory, the quark-hadron phase transition. Imagine trying to understand the properties of an ice cube by only studying steam. It sounds impossible because they're different states of the same substance. In the same way, the protons and neutrons we know and love are not fundamental. They are made of even smaller particles called quarks held together by gluons. For a fleeting moment after the Big Bang, the entire universe was so energetic that these quarks and gluons couldn't bind together at all. They existed as a seething, primordial soup known as a quark-gluon plasma, a state of matter so exotic we can only recreate it momentarily in the world's most powerful particle colliders. This theory suggests that the way this super-hot plasma cooled and condensed into the first stable particles, a process called the quark-hadron phase transition, could have been the real architect of the initial conditions for nucleosynthesis. It wasn't a gentle cooling, it was a dramatic change of state, like water vapor instantly freezing into a complex ice sculpture. The critical question is, was this transition smooth and even, or was it bumpy and chaotic? If it was the latter, it could have created profound imbalances. During this chaotic transition, some theories propose that strange and unstable forms of matter might have briefly existed. One fascinating idea is the formation of strangelets, hypothetical nuggets of strange quark matter containing a type of quark not found in ordinary matter. If these strangelets formed even for a nanosecond, they could have acted like cosmic sponges, soaking up neutrons and altering the delicate proton-to-neutron ratio that was so crucial for the nuclear reactions that followed just minutes later. A slight shift in that initial ratio would have sent ripples through the entire chain of creation, changing the final abundances of hydrogen, helium, and lithium in ways the standard model wouldn't account for. Think of it like a baker slightly altering the yeast-to-flour ratio at the very start of making bread. That tiny initial change results in a completely different loaf coming out of the oven. The quark-hadron phase transition theory posits that the recipe for the universe's first elements might have been written not during the 20 minutes of nucleosynthesis, but in the frantic hyper-energy chaos of that first microsecond. It connects the world of the impossibly small quantum chromodynamics directly to the chemical composition of the entire cosmos, suggesting that the secrets of our origins are buried even deeper than we once believed. Now, let's shift our focus from the chaotic soup of quarks to a far more elusive and ghostly component of the early universe, neutrinos. We've arrived at a theory that introduces a silent, invisible player that may have been subtly pulling the strings all along, the cosmic neutrino background influence. To understand this, we need to appreciate just how flooded the infant cosmos was with these particles. In the first second after the Big Bang, neutrinos weren't just present. They were one of the dominant forms of energy, outnumbering even protons and electrons by a factor of billions. This wasn't a small crowd, it was an overwhelming ocean, and crucially, these neutrinos weren't just passive spectators. They interact via the weak nuclear force, which, as the name implies, is incredibly feeble over distance but becomes immensely powerful at extremely close range, exactly the kind of conditions found in the ultra-dense early universe. During the crucial window of Big Bang nucleosynthesis, this sea of neutrinos was constantly streaming through the soup of protons and neutrons, and their weak interactions could have directly influenced the very first step in the entire chain reaction, the formation of deuterium. The key process involves a neutron. A free neutron is unstable and will decay into a proton, an electron, and an anti-neutrino in about 15 minutes. But the reverse is also true. A proton can absorb an electron and a neutrino to turn into a neutron. The rate of this conversion back and forth was governed by the density and energy of this neutrino background. If the sea of neutrinos was even slightly denser or more energetic than the standard model assumes, it would have shifted the delicate balance between protons and neutrons just before nucleosynthesis began. Think of it like a delicate chemical reaction in a lab. Even a slight change in temperature or pressure can dramatically alter the final product. In this case, a higher density of neutrinos would have meant more protons were converted into neutrons. Since helium nuclei are built from 2 protons and 2 neutrons, starting with a higher fraction of neutrons would mean the universe could have forged even more helium-4 than we currently predict. Conversely, a less influential neutrino background might have left behind more of the building blocks, resulting in a different cosmic composition. This theory suggests that the faint whisper of this primordial neutrino sea, a relic that still permeates all of space today, could hold the answer to those small but stubborn discrepancies in our models. What's truly captivating is that this isn't just speculative math. We have actually detected this cosmic neutrino background, albeit indirectly. Its existence is a firm prediction of the standard Big Bang model, and its imprint is seen in the large-scale structure of the universe and the anisotropies of the cosmic microwave background. So we know this ghostly sea is real. The unresolved question is whether its specific properties in those first few minutes were exactly as we've presumed, or if its subtle influence on the weak nuclear force has left a unique fingerprint on the universe's oldest elements that we are only now learning how to read. But our journey into the unconventional doesn't stop with ghostly particles. We now venture into a theory that is, by any measure, one of the most dramatic and speculative on our list, the primordial black hole disruption theory. To grasp this idea, we need to completely reframe our image of the universe's infancy. We often picture it as a smooth, if energetic, soup. But what if it was also littered with cosmic landmines, minuscule, incredibly dense objects known as primordial black holes? The concept is that in the first chaotic fraction of a second, immense pressures could have crushed some regions of space-time so violently that they collapsed directly into black holes. Unlike the stellar mass black holes formed from dying stars that we know today, these primordial ones could have been any size, from a microscopic speck with the mass of a mountain to something much larger. And according to this theory, these objects wouldn't have just been passive relics. They would have been active, violent engines of disruption during nucleosynthesis. Imagine the scene. The universe is trying to conduct the delicate symphony of forging the first nuclei, but scattered throughout the concert hall are these incredibly dense objects. Their immense gravity would warp the very fabric of space-time around them, creating localized bubbles of extreme conditions. In the immediate vicinity of a primordial black hole, the density of matter and the curvature of space would be radically different from the rest of the universe. Temperature, pressure, and even the flow of time itself would be distorted. Within these warped zones, the nuclear reactions of Big Bang Nucleosynthesis would not have proceeded according to the standard script. The frantic dance of protons and neutrons slamming together to form deuterium might have been accelerated to a fever pitch or perhaps stifled entirely. The half-life of a free neutron could have been effectively different. The entire carefully calculated chain of reactions that leads to a predicted abundance of lithium could have been thrown into disarray right at the source. This theory posits that what we observe today as the lithium problem, that frustrating gap between prediction and observation, might not be an error in our model of nuclear physics, but a fossilized record of these gravitational tornadoes ripping through the primordial soup. The beauty of this idea is that it offers a potential solution that doesn't require rewriting the fundamental laws of particle physics. Instead, it suggests that the environment itself was far more complex and textured than we assumed. It turns the early universe from a uniform laboratory into a landscape with dramatic features, where the history of element formation was written not by one set of rules, but by many, each dictated by its proximity to these terrifying and fascinating objects. While still highly speculative, this theory demonstrates the incredible lengths cosmologists will go to in order to solve a mystery, daring to use the most extreme objects in the universe as tools to decipher its gentle, ancient chemistry. This brings us to a theory so profound it challenges the very bedrock of physics as we know it, the variable constants hypothesis. We operate under a fundamental assumption that the laws of nature are immutable, that the numbers we plug into our equations, the strength of gravity, the mass of an electron, the force that holds atomic nuclei together, are the same today as they were at the dawn of time. It's a comforting notion, the idea of a consistent and reliable cosmos. But what if, in the extreme energy of the universe's birth, these so-called constants weren't constant at all? What if they were still settling into the values we measure today? This idea suggests that the stage for Big Bang nucleosynthesis might have had slightly different physical dimensions than we've always assumed. The most critical player in this drama is the strong nuclear force, the incredibly powerful glue that binds quarks together to form protons and neutrons, and then binds those protons and neutrons together to form atomic nuclei. Its strength is precisely tuned. If it were even a few percent stronger, protons would pair up so easily that hydrogen would be extremely rare, and the universe would be filled with helium and other elements from the start. If it were slightly weaker, no elements beyond hydrogen could form at all, and stars and planets would never exist. The variable constants hypothesis proposes that in the first few minutes, this force might have been fluctuating ever so slightly as the universe cooled from its unimaginably hot beginning. Even a tiny, temporary strengthening could have dramatically accelerated the rate at which deuterium fused into helium. Conversely, a momentary weakening could have left the process incomplete, leaving behind more deuterium than expected. This could elegantly solve the lithium problem. A specific, brief change in the strength of the nuclear forces could have provided a pathway for more lithium-7 to be destroyed, or less of it to be created, perfectly aligning the theoretical predictions with what we actually observe in the oldest stars. But the implications reach far beyond just a few elements. This theory touches on one of the deepest mysteries in all of science. Why do these fundamental constants have the exact values that they do? The values seem finely tuned for the existence of complex life, a fact that has led to speculation about a multiverse or even intelligent design. The variable constants hypothesis offers a different narrative. It suggests there was no fine-tuning at all, that the constants we measure are simply the frozen-in results of a random process of cosmic settling. They aren't special, they're just what was left when the music stopped. This turns a profound philosophical question into a dynamic physical process, a journey from chaos to order written into the very first atoms. This leads us to a theory that strikes at the very heart of one of cosmology's greatest puzzles, the mystery of matter itself. We call this the baryon inhomogeneous universe model, and to understand it, we first have to confront a profound cosmic asymmetry. According to our best models, the Big Bang should have created equal amounts of matter and antimatter. Yet when we look around, we see a universe made almost entirely of matter. The antimatter has vanished. The prevailing thought is that some unknown process, a phenomenon called baryogenesis, must have favored the creation of a tiny, tiny excess of matter. Just one extra particle for every billion matter-antimatter pairs that annihilated in a flash of energy. We are the descendants of that one in a billion imbalance. But this theory asks a terrifyingly beautiful question. What if that process wasn't smooth? What if that saving grace of matter wasn't distributed evenly like a fine mist, but was instead clumped and clustered like oil droplets in water? In this model, the infant universe wasn't a uniform sea of protons and neutrons. It was a chaotic, frothing ocean where regions rich in matter, what physicists call baryons, existed right alongside vast, empty voids where annihilation had been nearly total. This wasn't just a slight variation in density. It was a dramatic, fundamental patchwork of existence and near-nothingness. Now, place this radical idea into the context of nucleosynthesis. The entire process of building the first elements is exquisitely sensitive to one number above all others, the baryon-to-photon ratio. This number essentially tells you how much solid stuff is in the soup relative to the blinding energy of light. In the standard model, this number is assumed to be constant everywhere, but in an inhomogeneous baryonic universe, this ratio would have been wildly different from one region to the next. In a dense baryon-rich pocket, the ratio would be very high. There would be lots of protons and neutrons bumping into each other, leading to frantic, efficient fusion that would cook nearly all available fuel into helium, potentially even forging tiny amounts of heavier elements like carbon or oxygen far earlier than anyone thought possible. Conversely, in a sparse baryon-poor void, the ratio would be extremely low. Here, nucleosynthesis would be a sluggish, half-hearted affair. With fewer particles colliding, the process would be inefficient, leaving behind a much larger fraction of its original hydrogen and deuterium unfused. This single model, therefore, could simultaneously explain why we see slight variations in deuterium measurements from different ancient clouds, and why some pristine stars seem to have puzzlingly different initial chemistries. We wouldn't be looking at a single universal recipe, but rather the averaged-out result of billions of tiny, unique cosmic kitchens, each with its own distinct ingredient density. The most compelling aspect of this theory is that it doesn't require any new physics beyond what is already hypothesized to solve the matter-antimatter problem. It simply takes that existing puzzle and explores its logical, dramatic consequences. It paints a picture of a nascent cosmos that was fundamentally lumpy in its very composition, a place where the sheer existence of the material that would one day form stars and planets was itself a variable. This model suggests that the blueprint for the cosmic web of galaxies and voids we see today might have been drawn not just by gravity, but by the uneven distribution of existence itself in the universe's very first moments. But to add another layer of complexity to this neutrino puzzle, we must now consider that not all neutrinos are created equal. This brings us to our eighth theory, the lepton-flavored universe. We've established that the cosmic neutrino background was a dominant force, but we've been talking about them as if they were a single, uniform entity. In reality, neutrinos come in three distinct flavors: the electron neutrino, the muon neutrino, and the tau neutrino. They are not just different names, they have different masses and interact with matter in subtly different ways. The standard model of Big Bang nucleosynthesis makes a critical simplifying assumption that all three flavors were present in equal abundance and were in perfect thermal equilibrium with each other and the rest of the cosmic soup. But what if that wasn't the case? The lepton-flavored universe theory posits that the early universe might have had a profound preference for one type of neutrino over the others. Imagine a cosmic-scale preference for chocolate ice cream over vanilla and strawberry, but where that preference could alter the fundamental chemistry of creation. This flavor asymmetry would have had a direct and dramatic impact on the weak interaction processes we discussed earlier. The conversion rate of protons to neutrons is not identical for all neutrino types. It depends specifically on the density and energy of electron neutrinos and their antiparticles. If, for some unknown reason, the early universe was seeded with an overabundance of, say, muon or tau neutrinos, the delicate proton-neutron interconversion rates would have been skewed. An excess of electron antineutrinos, for instance, would have made it easier for protons to convert into neutrons, potentially leading to a higher initial neutron fraction and thus more helium production. Conversely, a deficit could have left the universe with more protons, preserving more of its primordial hydrogen. This isn't just a minor adjustment, it's a fundamental rewrite of the initial conditions. The different flavors could have decoupled from the thermal bath at slightly different times, each then free to influence nuclear reactions in its own unique way. This theory provides a fascinating new set of knobs to tweak in our cosmic model, knobs that could finally explain why our predictions for light elements are almost perfect but not quite. It suggests that the universe's first chapter might have been written not just in the language of physics, but with a specific dialect dictated by the subtle preferences of its most elusive particles. Now, let's turn our attention to a force that shapes the cosmos on the grandest scales, a force so familiar we rarely consider its potential role in the universe's very first moments: magnetism. We arrive at our ninth theory, which asks a startling question. What if powerful magnetic fields were present at the birth of everything? The primordial magnetic field's impact theory suggests that the infant universe might have been crackling with magnetism, and that this invisible force could have directly guided the assembly of the first atoms. We know that magnetic fields are everywhere today. They surround our planet, are woven through our galaxy, and thread the spaces between galaxy clusters. But their origin is a major unsolved puzzle. Were these fields created later by stars and galaxies, or were they there from the very beginning? This theory explores the latter, more profound possibility. Imagine the universe in its first few minutes, not just as a hot, dense soup, but as a soup swirling with immense primordial magnetic fields. These fields wouldn't have been the gentle ones we experience. They would have been unimaginably intense, perhaps billions of times stronger than anything in the modern cosmos. Why would this matter for making elements? Because the particles involved, protons, and the nuclei they form are not neutral. They are positively charged. And charged particles in a magnetic field don't move in straight lines, they spiral. They are forced into helical paths, corralled and guided by the invisible lines of magnetic force. This fundamental change in motion would have had a dramatic effect on the nuclear reactions. The rate at which two particles collide is everything in nucleosynthesis. If magnetic fields were present, they could have either focused particles together, increasing collision rates and speeding up fusion, or they could have confined them in ways that actually prevented them from ever meeting. Think of it like trying to navigate a crowded room. Without a magnetic field, it's a free-for-all. Particles zoom in every direction, bumping into each other randomly. But introduce a powerful magnetic field, and it's as if everyone is suddenly forced to walk along predetermined paths on the floor. Some paths lead directly to others, creating traffic jams of collisions. Other paths lead to dead ends or lonely corridors where encounters are rare. This theory proposes that the universe's first nuclear reactions might have occurred in a kind of organized magnetic labyrinth, not a chaotic free-for-all. This magnetic guidance system could have preferentially favored certain reaction pathways over others. It might have made the formation of deuterium more or less efficient, which would have cascaded through the entire chain, ultimately changing the final amounts of helium and lithium that survived. The stubborn lithium problem, in particular, might find its solution here. Perhaps the specific magnetic conditions provided a channel for lithium-7 to be broken apart more easily, or perhaps they suppressed its creation in the first place. This idea elegantly connects a large-scale cosmic phenomenon, magnetism, to the microscopic nuclear physics that built the periodic table, suggesting that the forces that shape galaxies today were also present in the workshop where the first elements were forged. Now we venture into a realm of physics that lies beyond the established standard model, a theory that introduces an entire shadow universe of particles that could have been the unseen architects of our elemental origins. This is the supersymmetric particle decay theory. To understand it, we must first grasp a profound ambition in modern physics, the dream of unification. Physicists have long sought a single, elegant framework that can describe all the fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces under one roof. One of the most promising candidates for this theory of everything is supersymmetry. Supersymmetry, often nicknamed SUSY, proposes a breathtakingly beautiful symmetry in nature. For every known particle in the standard model, every electron, every quark, every photon, there should exist a super-heavy superpartner. The electron would have a partner called the selectron, the quark, the squark, the photon, the photino. This isn't just a mathematical curiosity. It solves several profound problems in physics, such as the nature of dark matter and the puzzling weakness of gravity compared to the other forces. But most importantly for our story, if supersymmetry is real, then the early universe would have been teeming with these superpartners. it would have been a much richer, more complex, and more energetic place than our standard models assume. According to this theory, these supersymmetric particles, given their tremendous mass, would have been incredibly unstable in the newborn cosmos. They wouldn't have lasted long, decaying away into showers of lighter, standard model particles very quickly. But it's in that brief existence and their violent demise that the magic, or rather, the alternative physics, could have happened. Their decay would not have been a simple fade to black. It would have been a prolific event, injecting vast amounts of energy and exotic particles into the primordial soup right during the critical window of nucleosynthesis. Imagine the standard process of building elements as a carefully timed domino rally. Now picture someone tossing an extra handful of dominoes into the middle of the chain as it's falling. That's what sussy particle decay could have done. This sudden injection of energy and new particles could have drastically altered the temperature and density of the universe at precisely the wrong moment, throwing the delicate nuclear reaction rates completely out of whack. It could have provided entirely new pathways for elements to form, routes that are forbidden in standard physics. For instance, certain superpartners decaying could have produced an overabundance of specific particles that would have acted as catalysts, speeding up the fusion of deuterium or providing a shortcut to the formation of helium, bypassing the usual bottlenecks. This becomes a powerful tool for solving our lingering problems. That stubborn lithium discrepancy, perhaps the decay of a specific supersymmetric particle preferentially destroyed lithium's 7 nuclei as they formed, or perhaps it altered the proton-to-neutron ratio in a way that simply resulted in less lithium being created in the first place. The beauty of supersymmetry is that it isn't a single idea. It's a whole family of theories, each with different particles and different predicted decay signatures. This gives cosmologists a vast new set of parameters to play with, a virtual control panel of exotic physics that could be tuned to finally make our predictions perfectly match the ancient observational data we see etched in the stars. It suggests that the answers to the universe's oldest chemical mysteries might not lie in refining our current models, but in discovering a whole new layer of reality that has been hidden from us all along. But perhaps the most radical reimagining of the cosmos's fundamental architecture comes next, a theory that asks us to let go of our most basic perceptions of reality. We are about to explore the idea that the universe we see is merely a fraction of the whole, and that the true story of the first elements was written in a realm of higher geometry. This is the theory of extra dimensions influence. To begin, we must challenge a deep-seated intuition that our universe is made of 3 spatial dimensions: length, width, and height plus time. We move through this 3-dimensional world every second of every day, but for nearly a century, theoretical physicists have been captivated by the possibility that this is just the visible part of a much richer, multidimensional reality. String theory, one of the leading contenders for a theory of quantum gravity, requires the existence of at least 6 extra spatial dimensions, all curled up into a space so infinitesimally small that they are completely hidden from our view. Now apply this stunning concept to the Big Bang. In the very first instance, the universe was inconceivably small and energetic. According to this theory, those extra dimensions wouldn't have been curled up and hidden. They would have been open and active, playing a direct role in the physics of the cosmos. The fundamental forces, gravity, electromagnetism, and the nuclear forces might not have been the distinct entities we know today. In that higher dimensional arena, they could have been unified into a single master force. As the universe expanded and cooled, this master force would have undergone a process called spontaneous symmetry breaking, eventually crystallizing into the 4 separate forces we now observe. But the critical point is that this process might not have been fully complete during the epoch of nucleosynthesis. What does this mean for the first atoms? Everything. The strength of a force is governed by its coupling constants, fixed numbers that dictate how powerfully it interacts with matter. But if extra dimensions were still influencing physics, those constants might not have been constant at all. Gravity, which is incredibly weak in our three-dimensional world, might have been much stronger if it were allowed to leak into these additional dimensions. A stronger gravitational force in the early universe would have increased the expansion rate, dramatically altering the precious window of time available for nuclear reactions to occur. Faster expansion means less time for protons and neutrons to find each other and fuse. This could have shut down the nucleosynthesis process prematurely, leaving behind a much larger abundance of the initial fuel deuterium and creating far less of the end product helium. Conversely, if the strong nuclear force was also being modulated by these dimensions, its strength could have fluctuated, making it easier or harder for atomic nuclei to stick together. This provides a breathtakingly elegant potential solution to the lithium problem. A specific, temporary configuration of these extra dimensions could have subtly tweaked the nuclear cross-sections, the probabilities of particles interacting, just enough to suppress the formation of lithium-7 without significantly altering the yields of the other elements. This theory transforms our view of the cosmic dawn from an event governed by fixed rules into a dynamic, multidimensional ballet. The first elements become more than just relics of a nuclear process. They are fossilized imprints of a higher dimensional geometry that has since collapsed into hiding. It suggests that to truly understand the universe's first chapter, we might need to learn to read in more than 3 dimensions, deciphering a chemical story written in the language of higher mathematics and hidden spatial folds. But if we are to truly challenge the foundations of the Big Bang itself, we must consider a cosmology that rewrites the entire origin story. This brings us to our 12th theory, a concept so radical it does away with the singularity entirely, the ekpyrotic or brain collision theory. To understand this, we need to step away from the idea of a universe born from a single, hot, dense point and instead envision our reality as a 3-dimensional membrane, or brain, floating within a higher dimensional space. In this breathtaking model, the Big Bang was not a beginning, but an event, a violent collision between our brain and another parallel universe. Picture 2 immense, invisible sheets drifting slowly through a higher dimensional void. They approach each other, drawn together by gravity across a dimension we cannot perceive, and finally, they smash into one another. The energy of this cosmic collision is so incomprehensibly vast that it floods our 3-dimensional brain with matter and radiation, creating what we now observe as the hot, dense state of the early universe. This is the ekpyrotic scenario, a name derived from the Greek word for conflagration. In this model, our universe is cyclical, with brain collisions happening over and over again across eternity, each one setting off a new cosmic cycle. Now place the process of nucleosynthesis within this completely different Genesis story. The initial conditions would not be those of a rapidly expanding, cooling fireball from a singularity. Instead, the universe would be born from the debris of a collision, potentially with a very different distribution of energy, density, and even fundamental particles. The entire thermal history would be altered. The frantic 20-minute window for building the first elements might have been longer, shorter, or characterized by a completely different temperature profile. The proton-to-neutron ratio, that critical starting parameter, would have been set by the physics of the collision itself, not by the decay of a quark-gluon plasma. This opens up a universe of possibilities for explaining the anomalies. The lithium problem might simply vanish if the conditions of the brain collision naturally produced a lower abundance from the start. The slight discrepancies in deuterium measurements from different ancient gas clouds could be fossils from the uneven aftermath of the impact as energy and matter settled across our brain. This theory doesn't just tweak the parameters of the standard model, it provides an entirely new stage with a new set of rules upon which the drama of element formation could have played out. It suggests that the chemical fingerprints we are trying to decipher may not be from a unique birth, but from one event in an endless series of cosmic rebirths, each leaving its own subtle imprint on the elements that form the basis for the next cycle of stars, planets, and life. But what if the very fabric of space itself held a secret, dormant energy that flickered to life in the universe's first moments? This brings us to a theory that connects the destiny of the cosmos to its creation, proposing that the force that will one day tear the universe apart was also present at its birth, subtly guiding the handiwork of the first elements. We call this the quintessence field interaction. To understand it, we must first grapple with one of the greatest discoveries and mysteries of modern cosmology: dark energy. We now know that the expansion of the universe is not slowing down as once thought, but is actually accelerating. Some unknown repulsive force, dubbed dark energy, is pushing galaxies apart at an ever-increasing rate. The simplest explanation for this is Einstein's cosmological constant, a faint, unchanging energy inherent to the vacuum of space itself. But many physicists find this static concept unsatisfying. Instead, they propose that dark energy might be dynamic, a cosmic field that evolves over time. This hypothetical, evolving form of dark energy is known as quintessence, named after the fifth element of ancient philosophy. Now, here is the radical proposition. What if this quintessence field wasn't just a feature of the modern, old universe? What if it was also active and incredibly potent during the universe's fiery infancy? In the Standard Model, the expansion rate during nucleosynthesis is governed solely by the density of radiation and matter. But if a quintessence field was already present, its energy would have contributed to that density, acting as an extra source of gravity, or anti-gravity, that could have dramatically warped the evolution of the cosmos during those critical first minutes. Imagine the expansion of the universe as a dial controlling the time available for nuclear fusion. In the Standard Model, we know the dial's setting. But a quintessence field could have reached over and turned that dial. If this field was strong and positive in those early moments, it would have effectively added more oomph to the expansion, causing the universe to inflate faster. A faster expansion means the cosmos would have cooled more rapidly, slamming shut the precious window for nuclear reactions much sooner. This would have abruptly cut short the chain of fusion, potentially leaving behind a much larger fraction of the intermediate product, deuterium, while producing significantly less of the end product, helium. Conversely, if the quintessence field had a different character, perhaps even a negative energy density, it could have temporarily put the brakes on expansion, stretching out those 20 minutes into a longer, more leisurely period of cosmic alchemy. With more time to interact, particles could have fused more completely, cooking nearly all the available fuel into helium, and perhaps even allowing trace amounts of heavier elements like beryllium or boron to form, elements that the Standard Model says should be utterly impossible to create in the Big Bang. This dynamic field offers a beautifully elegant knob to adjust in our models. The persistent lithium problem, for instance, could be solved if a specific evolution of the quintessence field slightly altered the temperature curve at the exact moment lithium-7 was being formed, providing just enough of a change to suppress its production without throwing the carefully balanced abundances of hydrogen and helium into disarray. It suggests that the same mysterious force that determines the ultimate fate of the cosmos may also have written the very first lines of its chemical identity, linking the beginning of everything to its final, distant end in a single, continuous physical story. Now we venture into a theory that proposes the universe's first moments were not just hot and dense, but also fundamentally flawed, and that these flaws were the very things that guided the creation of the first elements. This is the cosmic string network theory. To grasp this, we need to stretch our imaginations to picture the fabric of space-time not as a smooth, featureless sheet, but as a material that can develop cracks and defects as it undergoes a dramatic phase transition. Think of it like this: when water freezes into ice, the process isn't always perfect. If it happens quickly, flaws and fractures can get locked into the crystal structure. In a very similar way, as the newborn universe expanded and cooled from an indescribably high energy state, physicists believe it may have gone through several radical phase transitions. The forces of nature were splitting apart, the fields that govern particles were settling into their current states, and just like the freezing water, this process might not have been perfectly smooth. It could have left behind incredibly exotic one-dimensional cracks in the very fabric of reality. These hypothetical defects are what we call cosmic strings. These wouldn't be strings in any ordinary sense. A cosmic string would be a filament of pure energy, thinner than a proton but of almost unimaginable density. A single inch of this stuff could weigh as much as a mountain, and according to this theory, the early universe wouldn't have had just one or two of them. It would have been filled with a vast, tangled network of these strings, a chaotic web of ultra-dense defects stretching across the entire cosmos. So how does a network of invisible, hyper-dense cracks influence the recipe for making atoms? It all comes down to gravity. Anything with that much mass warps the space around it. Each cosmic string would have been a gravitational tornado, creating a powerful well of distortion in its immediate vicinity. This means the universe during nucleosynthesis was not a uniform pot of soup. It was a pot simmering with countless gravitational whirlpools. In the regions of space near a string, the density of matter and the local curvature of space-time would have been drastically higher than in the regions far away from this tangled network. This patchwork of densities would have created a corresponding patchwork of temperatures and pressures. In a high-density region near a string, nuclear reactions would have proceeded at a feverish pace. Particles would have been squeezed closer together, colliding more frequently and fusing into helium with much greater efficiency. In the low-density voids between the strings, the opposite would be true. The expansion would have dominated, and the nuclear reactions would have been more sluggish and incomplete, potentially preserving more of the primordial deuterium and hydrogen. This offers a powerful and elegant way to resolve the lingering inconsistencies in our observations. The slight variations we see in the deuterium abundance from one ancient gas cloud to another might not be measurement errors at all. They could be the cosmic fossil record, telling us that one cloud formed from a region of space that was once near a dense cosmic string, while another cloud originated in a quiet void between them. The overall average we calculate might be correct, but the local reality was a rich tapestry of different chemical histories. The universe didn't have one single nuclear forge. It had billions of them, each operating under slightly different conditions dictated by its proximity to these ghostly scars from creation. This theory suggests that to read the first chemical chapter of the universe, we must learn to see the invisible cracks in the page it was written on. But what if the universe's first moments were not just a story of one type of matter, but two? This brings us to a hypothesis so strange it feels like science fiction, yet it is grounded in a deep and persistent puzzle in physics. We are about to explore the mirror matter-universe hypothesis. For decades, physicists have been perplexed by a curious asymmetry in the laws of nature. The weak nuclear force which governs radioactive decay and was so crucial in setting the proton-neutron balance seems to treat left and right differently. In a profound sense, the universe has a built-in handedness, a preference that breaks what physicists call parity symmetry. This discovery was so shocking it won a Nobel Prize. Yet, many theorists feel that at its most fundamental level, the universe should be balanced and symmetric. The mirror matter hypothesis is a breathtaking attempt to restore that balance. It proposes that for every particle we know, every electron, quark, and neutrino, there exists a perfect mirror image counterpart. This isn't antimatter, which is different. This is a whole parallel sector of particles, a shadow universe identical to our own in almost every way, but with one crucial difference. Its weak nuclear force would have the opposite handedness. In this mirror world, what we call left is right, and what we call right is left. The laws of physics would be perfectly symmetric after all, but that symmetry would be expressed across two separate, parallel cosmic realms that coexist within the same space as our own. Now place this incredible idea into the cauldron of the Big Bang. In the first few minutes, the energy was so unimaginably high that the barrier separating these two sectors might not have been absolute. Particles from our world and particles from the mirror world could have interacted, communicated, and influenced each other through new, unknown forces or via gravity, which is blind to such distinctions. This fleeting contact could have been the ghost in the machine of nucleosynthesis. The entire process is exquisitely sensitive to the number of light particle species present, as they affect how fast the universe expands and cools. The presence of an entire mirror sector, teeming with its own photons, neutrinos, and particles, would have effectively doubled the energy density of the universe during those critical first minutes. This would have dramatically increased the expansion rate. A faster expanding universe would have cooled more quickly, cutting short the time available for nuclear fusion. The consequences would be direct and measurable. Less helium-4 would be synthesized, and significantly more of the intermediate product, deuterium, would be left behind as unburned fuel. This is not a minor adjustment, it is a fundamental rewrite of the initial conditions. But the influence could have been even more nuanced. Perhaps specific mirror particles acted as catalysts or provided new pathways for nuclear reactions that don't exist in our standard model, subtly altering the branching ratios that determine how much lithium is produced versus destroyed. This elegant idea offers a powerful potential solution to the most stubborn problems. The observed deuterium abundance is a bit higher than some refined standard models predict, and the mirror universe's influence could neatly account for that. The lithium problem, that threefold discrepancy, might vanish if interactions with mirror particles opened up a new channel for lithium-7 to be destroyed or suppressed its formation altogether. The beauty of this theory is that it doesn't just solve one cosmological puzzle. It aims to solve several fundamental problems in particle physics at once, offering a candidate for the mysterious dark matter that holds galaxies together. Perhaps the mirror particles themselves are that missing mass. It suggests that the chemical fingerprints we are trying to decipher from the dawn of time may not be the product of our universe alone, but the result of a fleeting, ancient conversation with its own mirror image. But what if one of the most sacred constants in all of physics wasn't always so constant? We now turn to a theory that is perhaps one of the most radical and controversial on our entire list, a concept that challenges a fundamental pillar of Einstein's relativity itself. This is the varying speed of light cosmology, and it proposes a truly staggering idea: that the speed of light, that universal speed limit denoted by the letter c, was not always 299,792,458 meters per second. In the extreme conditions of the newborn cosmos, light itself may have raced across the universe at a vastly different pace, and that change would have rewritten every single equation we use to understand the Big Bang. To grasp why this is so revolutionary, we have to understand just how deeply the speed of light is woven into the fabric of our physical laws. It's not just the speed at which photons travel, it's a fundamental conversion factor between space and time, a critical component in the equations defining energy and mass, and the ultimate governor of causality, the speed at which any influence or information can travel through the cosmos. In our standard model of Big Bang nucleosynthesis, c is a fixed, unwavering number. All our predictions for the expansion rate, the cooling rate, and the available time for nuclear reactions are built upon that foundational assumption. Now imagine if that number was once much, much larger. If the speed of light was significantly faster in the universe's first few minutes, the consequences would be breathtaking. A faster speed of light would have fundamentally altered the expansion history of the cosmos. According to Einstein's equations, the expansion rate is intimately tied to the speed of light. A higher C would mean a much more rapid expansion in the earliest moments. This would have caused the universe to cool at a dramatically accelerated rate, slamming the window for nuclear fusion shut almost as soon as it opened. The frantic 20-minute window for building elements might have been compressed into just a few seconds. With so little time available, the chain of nuclear reactions would have been abruptly cut short. The result would be a universe left with a much larger abundance of the initial building blocks, particularly deuterium, and far less of the end product, helium. The observed elemental abundances, which so closely match the Standard Model's predictions, would be completely different. Conversely, what if the speed of light was momentarily slower? A reduced C would have put the brakes on the early expansion, stretching out those critical first minutes into a much longer, more leisurely epoch. With more time to interact, particles could have fused more completely. Nearly all the available hydrogen fuel would have been cooked into helium, potentially depleting the universe of the primary element needed to form future stars and water. It might have even allowed nuclear reactions to proceed further than we thought possible, forging tiny, trace amounts of heavier elements like beryllium or boron right from the start, elements that the Standard Model says simply could not have formed in the Big Bang. This radical idea is not just a wild thought experiment. It's a serious, albeit speculative, proposal put forward by some cosmologists to solve several profound puzzles. The most famous is the horizon problem, which asks how regions of the universe too far apart to have ever communicated with each other somehow manage to reach the exact same temperature. A period of faster-than-light travel in the very early universe, facilitated by a higher speed of light, could elegantly explain this uniformity. If this variable C phase occurred and then transitioned to our current constant speed, it would have left an imprint on everything that followed, including the process of nucleosynthesis. The tiny discrepancies we see, like the lithium problem, could be the direct result of this transition. Perhaps the shift to our current speed of light occurred just as lithium-7 was forming, subtly altering the nuclear cross-sections and leaving us with the lower abundance we observe today. This theory suggests that the most constant thing we know might have had a dynamic history, and that history is written into the very first atoms. But what if the very heartbeat of the early universe, its rate of cooling, was not the steady, predictable decline we've always assumed? This leads us to a theory that investigates the core thermal engine of creation itself, the thermal histories alternative. We often picture the universe's expansion and cooling as a smooth, uninterrupted process, like a hot oven being turned off and gradually reaching room temperature. This simple thermal history is baked directly into the mathematics of the Standard Model. But what if the cooling was uneven? What if the universe experienced thermal spikes or plateaus that dramatically altered the time available for the first nuclear reactions to play out? The entire chain of Big Bang nucleosynthesis is an exquisitely sensitive race against the clock, governed entirely by temperature. When the universe was too hot, above about 1 billion degrees, any newly formed deuterium nucleus would be immediately blasted apart by a high-energy photon. Only when the temperature dropped below this critical barrier could deuterium survive long enough to act as a stepping stone to form helium. The rate of cooling directly controls the duration of this crucial window. If the universe cooled faster than the Standard Model predicts, that window would have been shorter. The nuclear reaction chain would have been cut off prematurely, like turning off the stove before the water has fully boiled. The result would be a universe left with a great deal of unprocessed fuel, much more deuterium and much less helium than we expect. Conversely, imagine a scenario where the universe's cooling was somehow slowed or paused. Perhaps an early release of energy from decaying exotic particles or a temporary influence from a quintessence field put the brakes on the expansion just enough. This would have stretched out those critical 20 minutes into a much longer period. With more time to interact, the nuclear reactions would have proceeded further and more completely. Nearly all the available deuterium would have been efficiently cooked into helium-4, potentially depleting the universe of this crucial heavy hydrogen isotope. It might have even allowed the nuclear chain to venture slightly further, producing minuscule but measurable amounts of elements like beryllium or boron, which are completely absent from the standard Big Bang recipe. This theory offers a beautifully straightforward and powerful lever to pull when trying to solve our observational puzzles. The persistent discrepancy with lithium, for instance, could be neatly explained by a specific, non-standard cooling curve. Perhaps a brief, localized reheating event occurred right around the time lithium-7 was forming. This sudden spike in temperature could have provided just enough energy to break apart the fragile lithium nuclei as they formed, effectively erasing them from the cosmic record and leaving us with the lower abundance we see today. The beauty of exploring alternative thermal histories is that it doesn't necessarily require new particles or forces. It simply asks us to reconsider the timeline of the most fundamental process in cosmology, the expansion and cooling of space itself. It suggests that the universe's first elements are not just a product of physics, but a historical record of its very first moments of temperature change, a cosmic fossil of the infant cosmos's fever. Now we turn to a theory that focuses on a subtle but potentially monumental imbalance among the universe's most ghostly particles. This is the neutrino degeneracy theory, and it asks us to consider a scenario where the vast sea of neutrinos in the early cosmos wasn't just a uniform background, but a medium with a profound built-in preference, a chemical potential that favored matter over antimatter in its own ghostly realm. To understand this, we need to revisit the critical moment of weak interaction freeze-out, which occurred about 1 second after the Big Bang. At this instant, the universe cooled enough that neutrinos ceased interacting frequently with the rest of the particle soup. The rate at which a proton could convert into a neutron and vice versa plummeted. The final ratio of neutrons to protons was essentially locked in at this point, setting the absolute ceiling for how much helium could later form, since every helium nucleus requires 2 neutrons. The standard model assumes this neutrino sea was perfectly symmetric, with equal numbers of neutrinos and antineutrinos, and that this freeze-out happened under balanced conditions. But what if that symmetry was broken? Neutrino degeneracy refers to a hypothetical scenario where there was a significant asymmetry, a vast overabundance of, say, electron neutrinos compared to electron antineutrinos. This wouldn't be the matter-antimatter asymmetry we discussed earlier. This is a separate, specific imbalance within the neutrino sector itself. The consequences of such a degeneracy would be direct and dramatic for that all-important neutron-proton ratio. Remember the 2 key weak interaction processes. A neutron can decay into a proton, an electron, and an antineutrino, and a proton can absorb an electron and a neutrino to become a neutron. These are reversible reactions, and their equilibrium is like a delicate seesaw. An overabundance of electron neutrinos would heavily weight one side of that seesaw. It would make the conversion of protons into neutrons vastly more efficient. Everywhere you looked, protons would be eagerly absorbing the plentiful neutrinos and transforming into neutrons. If this happened, the universe would have entered the nucleosynthesis epoch with a much higher fraction of neutrons than the standard model predicts. Since helium-4 is such a stable and efficient nucleus to form, all those extra neutrons would have been swiftly incorporated. The result would be a universe with a significantly higher primordial abundance of helium. Instead of the predicted 25% by mass, we might be looking at 30% or even more. Conversely, a degeneracy in the opposite direction, a surplus of antineutrinos, would have had the opposite effect, suppressing neutron formation and leaving the cosmos with a helium-poor, hydrogen-rich composition. This theory provides a remarkably precise dial to adjust in our cosmic models. The observed helium abundance is one of the key pillars supporting the standard model, but it's not without its own tiny uncertainties. Perhaps a small degree of neutrino degeneracy is the reason for those slight variations. More compellingly, this idea doesn't operate in a vacuum. The same neutrino degeneracy that could alter helium production would also leave a distinct imprint on the cosmic microwave background and the large-scale structure of the universe. This means we might one day be able to test this hypothesis not just by looking at the oldest stars, but by studying the faint afterglow of the Big Bang itself, searching for the ghostly signature of an ancient particle imbalance that shaped the very chemistry of creation. This brings us to a theory that reimagines the primordial cosmos not as a serene, simmering soup, but as a churning, chaotic cauldron of cosmic weather. We call this the primordial turbulence model, and it proposes that the first elements were forged not in a placid laboratory, but in a hyper-violent blender of swirling plasma. To grasp this, we need to abandon the image of a perfectly smooth, expanding fireball and instead picture a universe in its first minutes as a superheated, ultra-dense fluid, subject to the same fundamental forces that create hurricanes and ocean currents. In this turbulent vision, the infant universe was not calm. Immense pressures and temperature gradients, left over from inflation or from the quark-hadron phase transition, would have whipped the particle plasma into a frenzy of vortices and eddies. Think of a pot of water just as it reaches a rolling boil, with massive bubbles of vapor rising and chaotic currents swirling in every direction. Now magnify that turbulence to a cosmic scale, with currents of energy and matter moving at relativistic speeds. In this environment, different parcels of the cosmic fluid would have had slightly different histories. One pocket might have been slightly hotter and denser, another slightly cooler and more diffuse. Under perfectly calm conditions, these regions would have remained isolated, each cooking its own unique blend of elements according to its local conditions. But turbulence changes everything. It is the great cosmic mixer. This violent churning would have torn these isolated pockets apart and slammed them into one another, creating a dynamic, ever-changing mosaic where regions that finished nucleosynthesis early were forced to mingle with regions that were still in the throes of fusion. It's the difference between baking a dozen separate, unique cupcakes and throwing all the ingredients into a single industrial mixer. The final batter is a uniform average, but it doesn't truly represent any of the individual recipes that went into it. This continuous and frantic mixing would have profoundly altered the final observed abundances of the light elements. The deuterium that formed efficiently in a cool, quiet pocket might have been violently injected into a super-hot, dense vortex where it was instantly ripped apart. Conversely, a region that had managed to produce a tiny amount of an element like lithium-7 might have had that yield dramatically diluted when it was mixed into a vast volume of lithium-poor plasma. The entire universe would have been homogenized, but the resulting average would be different from the yield predicted by a model that assumes a perfectly smooth and calm expansion from the start. This offers a beautifully physical and dynamic solution to several puzzles. The slight variations we see in deuterium abundance from one ancient gas cloud to another might not be measurement errors. They could be the last remnants of incomplete mixing, tiny fossils of a time when the universe hadn't yet finished stirring its own primordial batter. The infamous lithium problem could be explained if this turbulent mixing preferentially transported lithium-7 into regions where it was more easily destroyed, or if it averaged out extremely high production in some areas with zero production in others, resulting in a lower overall abundance than any uniform model could predict. This theory suggests that to read the universe's first chemical ledger, we must account for the stormy weather that was churning the pages as they were being written. Now we arrive at a theory that questions one of the most fundamental forces governing the cosmos, gravity itself. This is the modified gravity theory's impact, and it dares to ask a profound question. What if our understanding of gravity, the very architect of the universe's expansion, is incomplete? For nearly a century, Einstein's theory of general relativity has been the unshakable foundation of cosmology. It tells us that gravity is the curvature of space-time by mass and energy, and it provides the equations that describe how the universe expands. Our entire model of Big Bang Nucleosynthesis is built upon this specific expansion history. But what if gravity behaves differently under certain conditions, and we've been using the wrong map to chart the universe's earliest moments? This idea isn't as far-fetched as it might seem. In the modern universe, we have a glaring problem. The motions of stars within galaxies suggest there is far more gravity at work than can be accounted for by the visible matter. We call the source of this missing gravity dark matter, and it's the prevailing solution, but a small group of physicists proposes a radically different answer. Perhaps there is no dark matter. Instead, perhaps our laws of gravity are simply wrong on the scale of galaxies. This idea is known as modified Newtonian dynamics, or MND. While MND was initially proposed to fix galaxy rotation curves without dark matter, its implications would ripple all the way back to the Big Bang, completely rewriting the story of the first elements. To understand how, we need to see gravity as the conductor of the cosmic orchestra. The expansion rate of the universe during its first few minutes is the master tempo, controlling how much time is available for nuclear fusion to occur. In the Standard Model, this expansion rate is dictated by general relativity and the presumed presence of dark matter. But in a MND-like modified gravity scenario, the force of gravity would have a different strength, especially in the extremely low-density environment of the early universe. This would fundamentally alter the expansion history. A stronger effective gravity would have made the young universe contract more powerfully, potentially slowing its initial expansion. A weaker gravity would have allowed it to fly apart more rapidly. Either change would adjust the precious countdown clock for nucleosynthesis. Imagine the difference between trying to cook a complex meal with a timer that is accurate versus one that randomly speeds up and slows down. If modified gravity caused the universe to expand more slowly than general relativity predicts, the cooling would have been more gradual. That frantic 20-minute window for building elements would have been stretched into a longer, more leisurely period. With more time for particles to interact, nuclear reactions would have proceeded further and more completely. Nearly all the available deuterium would have been efficiently fused into helium, potentially leaving the universe with a severe shortage of the heavy hydrogen needed to fuel the first stars. Conversely, if modified gravity caused a faster expansion, the window would have slammed shut prematurely, cutting the fusion chain short and leaving behind a much larger fraction of unprocessed deuterium and far less helium. This provides a powerful and elegant potential key to unlock our persistent observational puzzles. The slight but nagging discrepancies in deuterium measurements from different ancient clouds could be a direct signature of a non-standard expansion history. The infamous lithium problem might simply vanish if the altered expansion rate under modified gravity provided just the right conditions for lithium-7 to be destroyed more efficiently as it formed. This theory is breathtaking in its scope because it doesn't just add a new variable to the existing model. It suggests that the entire foundational framework we use to calculate the first 3 minutes might be resting on an incomplete understanding of the universe's most familiar force. It proposes that the answers we seek are not to be found in exotic new particles, but in a deeper, more nuanced law of gravity that has been hidden in plain sight all along. But to truly appreciate the role of an unseen actor in this cosmic drama, we must now turn our attention to the most mysterious substance in the universe, one that has so far only revealed itself through its ghostly gravitational pull. This brings us to a theory that suggests dark matter was not merely a silent spectator in the early cosmos, but an active participant that may have literally warmed the pot in which the first elements were cooked. We call this the dark matter annihilation influence, and it proposes that the very particles that make up the invisible bulk of our universe could have briefly stolen the show during nucleosynthesis. For decades, the primary evidence for dark matter has been gravitational. We see its effects in the way galaxies spin too fast to hold themselves together and in the way light bends around massive clusters. The prevailing view is that dark matter is cold and collisionless, meaning it doesn't interact with light or with itself. It simply forms the gravitational scaffolding upon which the visible universe is built. But many theories that attempt to explain what dark matter actually is, such as the popular WIMP or weakly interacting massive particle, predict that these particles aren't entirely inert. They could be their own antimatter counterparts. This means that when two dark matter particles collide, they could annihilate each other in a flash of pure energy, converting their mass into standard model particles like electrons, protons, and photons. Now, rewind the clock to the universe's first few minutes. The cosmos is incredibly dense, and dark matter isn't just out in the halos of future galaxies. It's everywhere, mixed homogeneously with the primordial plasma of protons, neutrons, and electrons. In this ultra-dense environment, the rate of dark matter particle collisions would have been astronomically high. According to this theory, these constant annihilations would have acted like millions of tiny microwave ovens scattered throughout the soup, constantly injecting bursts of energy and heat into the plasma. This wouldn't have been a gentle warming, it would have been a significant and sustained source of extra energy, fighting against the natural cooling driven by the expansion of the universe. This injection of energy would have fundamentally altered the thermal history of the cosmos during the critical nucleosynthesis window. The entire process of building elements is a race against the clock of cooling. The moment the universe drops below 1 billion degrees, deuterium can finally form without being immediately blasted apart. But if dark matter annihilations were persistently pumping heat into the plasma, they could have kept the universe above that critical temperature for a fraction longer than the standard model predicts. This would have effectively delayed the start of the nuclear fusion chain reaction. A delay of even a few seconds might not sound like much, but in the frantic 20-minute timeline of Big Bang Nucleosynthesis, it is an eternity. During that delay, more free neutrons would have had time to radioactively decay into protons, subtly shifting the initial proton-to-neutron balance. The consequences of this shift ripple through the entire chain. A lower initial neutron fraction means less fuel is available to build helium nuclei. The final abundance of helium-4 would be slightly reduced. Simultaneously, the delayed start means the expansion of the universe has progressed further by the time fusion finally begins, leaving less time for the nuclear reactions to run to completion. This could result in more of the intermediate product, deuterium, being left behind as unburned fuel. This theory, therefore, offers a potential explanation for why some of the most precise observations of ancient gas clouds seem to show a deuterium abundance that is a tiny bit higher than the most refined standard models predict. The annihilations of the universe's most mysterious component could have literally left more heavy hydrogen on the cosmic table, but the influence could be even more nuanced and dramatic. This heating wouldn't have been perfectly uniform. Denser clumps of dark matter would have experienced more frequent annihilations and thus more intense local heating. This could have created a patchwork of slightly different thermal environments throughout the cosmos, a scenario that echoes the inhomogeneous models we discussed earlier. In these superheated pockets, nuclear reaction rates might have been suppressed entirely, while in cooler regions nearby, they may have proceeded normally. The observed elemental abundances we measure today would then be a complex average of these wildly different local conditions, a fossilized record of dark matter's first and most dramatic interaction with the visible universe, an interaction that faded away as the universe expanded and the dark matter particles became too spread out to find each other and annihilate anymore. Yet to truly rewind the clock to its absolute limit, we must confront a barrier that stands as the ultimate frontier of human knowledge, the very beginning of time itself. This brings us to a theory that stretches our understanding of reality to its breaking point, venturing into a domain where space and time cease to have any familiar meaning. We are about to explore the quantum gravity effects theory, a concept that suggests the universe's first elements were imprinted with the faint, fuzzy signature of its own birth, a signature written in the language of quantum gravity. To even approach this idea, we must first grapple with the Planck epoch, a period so early that it makes the quark-gluon plasma seem recent. We are talking about the first 10 to the minus 43 seconds after the Big Bang. At this incomprehensible scale, the energy density was so extreme that the quantum fluctuations governing the subatomic world and the gravitational force shaping the cosmos were no longer separate phenomena. They were one and the same. Our two most successful but utterly incompatible theories, quantum mechanics and general relativity, must merge into a single, unified framework, a theory of quantum gravity. We don't have this complete theory yet. Candidates like string theory and loop quantum gravity are our best attempts. But this theory proposes that whatever the true nature of quantum gravity, its effects didn't just stay locked in that first instant. They rippled forward in time, cascading down through the ages to subtly influence the nuclear reactions that built the first atoms. Imagine the fabric of space-time at this scale not as a smooth, continuous sheet, but as a seething, frothing foam of virtual particles popping in and out of existence, with the very concepts of here and now becoming blurred and uncertain. In this quantum foam, the fundamental constants of nature, the mass of the electron, the strength of the nuclear forces, might not have been fixed. They could have been subject to tiny, random fluctuations, flickering in and out of different values like a candle in the wind. These wouldn't be the organized variations of earlier theories. These would be primal, chaotic tremors in the bedrock of reality itself. Now, fast forward those tremors just a few minutes to the epoch of nucleosynthesis. The entire process is a precise clockwork mechanism dependent on exquisitely fine-tuned parameters. The probability that two particles will collide and fuse, known as a nuclear cross-section, is not a suggestion. It's a hard number determined by the fundamental constants. But what if that number was still settling down? What if quantum gravitational fluctuations had temporarily tweaked the strength of the strong nuclear force by just 1 part in a billion? Such a tiny, transient change could have had a monumental impact. A momentary strengthening could have dramatically accelerated the rate at which deuterium fused into helium, effectively shortening the available time for other reactions to occur and altering the final balance of elements. This becomes a profoundly elegant potential solution to the most stubborn puzzles. The lithium problem, that persistent threefold discrepancy between prediction and observation, might not be an error in our nuclear physics. It could be a direct fossil, a cosmic fingerprint left by a random quantum gravitational fluctuation that occurred in the first instant of time. A fluctuation that slightly suppressed the production of lithium-7 before the constants settled into their current, stable values. The universe's elemental abundance would then be not just a product of known physics, but also a record of its own chaotic and fuzzy birth, a message from a time before time where the laws of physics as we know them were still being forged. This theory suggests that to finally understand why the cosmos is made the way it is, we may need to learn to read the subtle quantum whispers from the very moment of creation. But what if the primordial soup didn't just cool down smoothly, but passed through a phase so exotic that it fundamentally changed the nature of matter itself? This brings us to a theory that delves into the deepest principles of particle physics, a concept known as the Hagedorn phase transition hypothesis. To understand this, we need to introduce a fascinating and counterintuitive idea, a temperature so high that it represents an absolute limit, a cosmic heat barrier beyond which conventional matter cannot get any hotter. This isn't the speed of light, it's a thermal ceiling, and it's named the Hagedorn temperature after the physicist who first proposed its existence. Imagine trying to heat a pot of water on your stove. As you add energy, the water gets hotter and hotter until it reaches 100 degrees Celsius, and then it begins to boil, transforming from a liquid into a gas. This is a phase transition. Now, apply this concept to the very fabric of matter. The Hagedorn temperature, estimated to be around 2 trillion degrees, is thought to be the point at which hadronic matter, the protons and neutrons that make up atomic nuclei, undergoes its own incredible phase transition. Just as liquid water can't exist above 100 degrees, protons and neutrons might not be able to exist as distinct entities above 2 trillion degrees. Instead of getting hotter, any additional energy pumped into the system would not raise the temperature, but would instead be used to create new particles, spawning a vast and growing zoo of exotic hadrons in a phenomenon known as a fireball. Now rewind the universe to its first microseconds. The temperature is plummeting from far above the Hagedorn limit down through this critical threshold. According to this hypothesis, this wasn't a simple cooling. It was a dramatic and tumultuous change of state. As the universe fell through the Hagedorn temperature, the chaotic fireball of exotic particles would have suddenly and rapidly condensed back down into the familiar protons and neutrons that would become the feedstock for nucleosynthesis. But here's the critical twist. This phase transition might not have been instantaneous and uniform across the entire cosmos. It could have occurred in pockets or been subject to supercooling and sudden bursts of nucleation, much like a supercooled cloud suddenly flash freezing into ice crystals. This uneven and potentially turbulent transition could have created profound local variations in the density and ratio of protons to neutrons. In some regions, the condensation might have been exceptionally efficient, creating a higher local density of baryons and setting the stage for a more vigorous period of nuclear fusion just minutes later. In other regions, the process might have been less complete, leaving behind a more dilute soup. This provides a compelling physical mechanism for the kind of inhomogeneous conditions we discussed in earlier theories, but with a specific and testable origin point rooted in the fundamental physics of hadrons. The implications for nucleosynthesis are profound. A universe passing through a Hagedorn phase transition would have had its initial conditions for element formation set not during the quark-hadron transition, but during this later hadronic event. The specific pathways available for nuclear reactions are highly sensitive to the density of particles. In a dense region born from a rapid Hagedorn condensation, the nuclear reaction chain might have been pushed further, potentially creating tiny amounts of elements beyond lithium, like beryllium or even boron, in direct contradiction to the standard model. Conversely, the chaotic particle production near the Hagedorn limit could have provided entirely new routes for elements to form or be destroyed, routes that are simply not present in a smooth, transition-free model of the cooling universe. This theory suggests that the ultimate recipe for the universe's first atoms was finalized not in the first 3 minutes, but in the frantic instance when matter itself changed its fundamental nature at 2 trillion degrees. Yet, even as we consider the profound influence of unseen dimensions and cyclical collisions, we must confront perhaps the most fundamental asymmetry of all, the very existence of matter itself. This brings us to a theory that doesn't just tweak the conditions of the early universe, but seeks to explain why there is anything here to tweak at all. We are now exploring the Affleck-Dine baryogenesis connection, a concept that dares to link the mystery of our existence to the specific chemistry of the first elements. To appreciate this idea, we must return to that most profound of cosmic puzzles. Why does anything exist? According to our best understanding of physics, the Big Bang should have created precisely equal amounts of matter and antimatter. These opposite counterparts would have then annihilated each other in a flash of pure radiation, leaving behind a universe devoid of stars, planets, or people. The fact that we are here means this perfect symmetry was broken. Some process known as baryogenesis must have created a tiny 1 in a billion excess of matter over antimatter. We are the result of that 1 in a billion imbalance. The Affleck-Dine mechanism proposed by physicists Ian Affleck and Michael Dine is one of the most compelling explanations for how this happened. It suggests that in the supremely energetic early universe, exotic new scalar fields, cousins to the famous Higgs field, were activated. These fields, as they evolved and rolled down their energy landscapes, could have preferentially created matter over antimatter, seeding the cosmos with the initial imbalance we see today. But this theory proposes something even more remarkable. This same process didn't just create the raw material for the universe, it also directly tampered with the recipe for the first elements. Imagine the Affleck-Dine mechanism not as a silent, behind-the-scenes event, but as a cosmic scale factory. As these scalar fields evolved, they wouldn't have just produced a smooth mist of matter. They would have generated intense waves of energy and potentially even entirely new, short-lived particles as byproducts. This energetic fallout would have been injected directly into the primordial plasma right during the critical window of nucleosynthesis. It's the difference between quietly adding an ingredient to a recipe versus tossing it into a pot that's already boiling vigorously. The sudden injection of energy and new particles would have violently disturbed the delicate thermal equilibrium, locally reheating regions of the universe or providing new pathways for nuclear reactions. This becomes a powerful tool for solving our persistent elemental puzzles. That stubborn lithium problem, for instance, might find its solution here. The decay products of these Affleck-Dine fields could have included particles that acted as catalysts, specifically destroying lithium-7 nuclei as they formed or altering the proton-to-neutron ratio in a way that suppressed its production from the start. Similarly, the slight variations we see in deuterium abundance from different ancient gas clouds could be the fossilized imprint of this uneven injection of energy. Some regions of space were closer to the factories of the Affleck-Dine field, and thus experienced a more violent disruption of their nucleosynthesis process than others. The profound beauty of this theory is its elegant economy. It doesn't invent a new phenomenon to explain the light elements. It uses a phenomenon that we arguably need to explain our own existence. The Affleck-Dine mechanism, or something like it, is required to answer the question of why we are here. This theory simply suggests that while solving that ultimate mystery, it left its fingerprints all over the universe's first chemistry set, subtly altering the abundances of hydrogen, helium, and lithium in ways that we are only now beginning to decipher. It proposes that the answers to two of cosmology's greatest puzzles, why we exist and why the universe is made the way it is, might be forever intertwined, written into the cosmos in the same ancient script. But to venture even further beyond our standard cosmic timeline, we must now consider a possibility that redefines the very meaning of the beginning. This is the pre-Big Bang cosmology model, a theory that dares to suggest our universe was not born from a singularity, but instead emerged from the ashes of a previous cosmic era, a phase of contraction that came before the expansion we observe today. In this breathtaking scenario, the Big Bang was not a true beginning but a dramatic turning point, a moment of cosmic rebirth known as the Big Bounce. And if that is true, then the entire set of initial conditions for nucleosynthesis, the temperature, density, and composition of the infant universe, would have been inherited from the death throes of its predecessor, offering a completely new set of rules to explain the formation of the first elements. Imagine the entire universe not expanding, but instead slowly and inexorably collapsing in on itself over billions of years. Galaxies would draw closer together, the background temperature of space would steadily rise, and eventually, all matter and energy would be compressed into an incredibly hot, dense state. In the standard model, this collapse would end in a singularity, a point of infinite density where physics breaks down. But in certain quantum gravity models, this collapse might be arrested just short of that point. The immense repulsive force of quantum gravity could kick in, causing the universe to rebound and begin expanding again in the event we call the Big Bang. Our universe, in this view, is simply the latest cycle in an endless series of cosmic contractions and expansions stretching eternally into the past and future. Now place the process of nucleosynthesis within this cyclical framework. The standard model starts with a set of pristine, simple initial conditions, a hot, dense soup of quarks, leptons, and radiation expanding from a singular origin. But a universe that has bounced carries the baggage of its past life. The matter and energy present at the moment of the bounce wouldn't be primordial and pure, they would be the processed remnants of a previous cosmic cycle. That previous universe would have lived a full life. Its stars would have been born, fused elements in their cores, and died in supernova, enriching the cosmos with heavy elements. When that universe contracted, all that stardust, all the complex atoms of carbon, oxygen, and iron, would have been crushed back together into a superheated plasma. This means that at the start of our Big Bang, the primordial soup might not have been just hydrogen and helium. It could have been seeded with traces of every element in the periodic table, a fossil inheritance from the stars of a forgotten cosmos. This would completely upend the clean narrative of Big Bang nucleosynthesis. The nuclear reactions in the first 20 minutes would not have started with a blank slate. They would have occurred in a medium that already contained heavier atomic nuclei. These pre-existing nuclei could have acted as catalysts, opening up entirely new nuclear reaction pathways that are forbidden in the standard model. They could have absorbed neutrons, altering the delicate balance required to form deuterium and helium, or they could have provided surfaces for more complex molecules to begin forming almost immediately. The observed abundances of the light elements would then be a complex blend of new production from the rebound and the recycled remains of a prior universe. The famous lithium problem might find a natural solution here. Perhaps the lithium we see today isn't purely primordial at all, but is partly a relic carried over from the previous cycle, its abundance set by the final generations of stars that lived before the Great Contraction. This model transforms the first elements from simple starting points into a profound link in an infinite cosmic chain, suggesting that the universe's original chemistry was not original at all, but was built upon the ashes of countless universes that came before. Now we prepare to venture into perhaps the most metaphysically daring theory on our list, a concept that challenges our most basic perception of reality's very structure. This is the holographic principle application, an idea proposing that the entire three-dimensional universe we experience, with all its vastness and complexity, might be nothing more than a projection, a cosmic illusion encoded on a distant two-dimensional surface. And if this is true, then the process that forged the first elements wasn't just governed by local physics, but was constrained by the information capacity of the universe's ultimate boundary. To begin wrapping our minds around this, let's use a familiar, though imperfect, analogy. Think of a hologram like the one on your credit card. It's a flat, two-dimensional surface, but when you tilt it, it creates the stunning illusion of a three-dimensional image floating in space. The holographic principle applies this same concept to the entire cosmos. It suggests that all the information that describes every star, every planet, and every one of us, every bit of matter and energy in our three-dimensional universe, is actually encoded on a vast, two-dimensional boundary that surrounds us like the surface of a giant bubble. Our reality isn't the primary thing. It's a projection, a shadow cast from the edge of space-time itself. This isn't just philosophical speculation. It's a serious proposal that emerges from the study of black holes and attempts to reconcile gravity with quantum mechanics. A black hole's entropy, which is a measure of its information content, is proportional not to its volume, as you might expect, but to the surface area of its event horizon. This startling discovery led physicists like Gerard T. Hooft and Leonard Susskind to wonder, if a black hole's information is stored on its surface, could the same be true for the entire universe? The holographic principle answers with a resounding yes, implying that there is a fundamental limit to how much information any region of space can contain, a limit defined by its surface area, not its volume. Now, rewind this incredible idea back to the universe's first few minutes. During Big Bang Nucleosynthesis, the cosmos was an unfathomably dense and hot nuclear reactor. In the Standard Model, the reactions that produced hydrogen, helium, and lithium were governed by local conditions, temperature, density, and the fundamental nuclear cross-sections. But the holographic principle introduces a profound and global constraint. It suggests that the number of degrees of freedom, the number of ways particles could be arranged and interact, was not infinite. The total amount of information available to describe all the quantum states of all the particles in that primordial fireball was capped by the surface area of the observable universe at that moment. This fundamental information limit could have acted as a cosmic regulator on the nucleosynthesis process. Nuclear reactions at their heart are about probabilities and the number of available quantum states for particles to occupy. If the holographic principle is correct, the number of these available states would have been strictly limited by the information capacity of the universe's two-dimensional boundary. This constraint might have subtly influenced the statistical likelihood of certain nuclear reactions occurring, effectively putting a soft ceiling on how efficiently particles could find each other and fuse. It's as if the universe was running a complex simulation, but the processing power of its cosmic computer was limited by its two-dimensional architecture, forcing certain outcomes over others. This provides a breathtakingly elegant and deeply fundamental potential explanation for the precise ratios of the light elements we observe. The famous lithium problem, for instance, might not be a problem with our nuclear physics, but a signature of this information theoretic constraint. The specific pathway that leads to the production of lithium-7 might have required more quantum information than the holographic boundary could encode or process at that specific moment in cosmic history, leading to a suppressed yield. Similarly, the near-perfect agreement on helium and deuterium could be seen as the natural outcome of nuclear processes that fit perfectly within the universe's informational budget. The elemental abundances we measure today would then be more than just a relic of nuclear physics. They would be a direct reflection of the deepest informational architecture of reality, a fossilized imprint from the moment the universe projected its first three-dimensional shadows. But to truly challenge our understanding of the universe's fundamental building blocks, we must venture into a theory that replaces the point-like particles of the Standard Model with tiny, vibrating loops of energy. This is the string gas cosmology approach, a vision of the cosmos where the initial state wasn't a hot soup of quarks, but a dense, tangled gas of fundamental strings, and where this radical starting point completely rewrites the thermal history that governs the formation of the first elements. String theory itself proposes that at the most fundamental level, everything in the universe, every particle, every force carrier, is not a zero-dimensional point, but a one-dimensional, oscillating filament of energy. The different vibrations of these strings give rise to the different properties of the particles we observe. String gas cosmology takes this beautiful idea and applies it to the very beginning of everything. It suggests that before the Big Bang as we imagine it, the universe was filled with a hot, dense gas of these fundamental strings, all interacting and vibrating in a space that had not yet settled into the three extended dimensions we experience today. In this model, the universe might have started with all 9 spatial dimensions predicted by string theory being small and compact. The strings winding around these compact dimensions would have provided a stabilizing force preventing a catastrophic collapse. As this string gas evolved, only 3 of those dimensions were destined to expand rapidly to become the vast universe we see, while the others remained curled up into the tiny, hidden spaces we now postulate. This entire process, the unwinding of the strings, the stabilization of the dimensions, and the eventual heating of the universe results in a thermal history that is profoundly different from the standard Big Bang model. The cosmos wouldn't have begun in a state of infinite temperature and density. It would have had a maximum temperature, a fundamental limit set by the string scale itself. This alternative thermal history is the key to understanding how string gas cosmology alters the story of nucleosynthesis. The entire process of building the first elements is a precise race against the clock of cooling. In the standard model, the universe expands and cools in a very specific, predictable way. But in the string gas scenario, the expansion rate and the cooling curve could be dramatically different. The transition from a hot string gas to a radiation-dominated universe might have been more gradual, or it might have included phases of slower or faster expansion dictated by the dynamics of the strings themselves and their winding modes around the compact dimensions. A different expansion rate means a different amount of time available for nuclear fusion to occur before the universe becomes too cold and diffuse for reactions to continue. If the string-derived expansion was faster than in the standard model, the window for nucleosynthesis would have been shorter. This would have abruptly cut off the nuclear reaction chain, leaving behind a much larger fraction of the intermediate product, deuterium, as unburned fuel, while producing significantly less of the end product, helium. Conversely, a slower expansion rate in the string gas scenario would have stretched out those critical 20 minutes, allowing fusion to proceed further and more completely, potentially cooking nearly all the available deuterium into helium and leaving the universe with a severe shortage of the heavy hydrogen so crucial for forming the first stars. This provides a powerful new parameter space to explore when trying to solve the lingering observational puzzles, particularly the slight but nagging discrepancies in the measured deuterium abundance from ancient clouds. Furthermore, the string gas itself could have provided novel mechanisms for element formation. The interactions of these fundamental strings, their splitting and joining, could have generated unique signatures or even entirely new particles in the early plasma. These exotic entities might have acted as catalysts for nuclear reactions, opening up pathways that are simply forbidden in the standard model of particle physics. The specific vibrational modes of the strings could have influenced the effective strengths of the fundamental forces during those first few minutes, subtly altering the nuclear cross-sections that determine the probability of two particles fusing. The infamous lithium problem, that threefold discrepancy between prediction and observation, might vanish if the unique physics of a string gas universe provided a natural channel for lithium-7 to be destroyed more efficiently or suppressed its production from the start. This theory suggests that the answers to the universe's oldest chemical mysteries are not to be found by refining our current models, but by listening to the faint, vibrational echoes from a time when the cosmos was a symphony of fundamental strings. This concept takes us back to the very first theory we explored, but with a profound and cosmic twist. While the standard Big Bang Nucleosynthesis model assumes a singular beginning from a pristine, hot state, the cyclic universe model proposes something far more grand and eternal. Imagine not a single birth, but an endless cosmic heartbeat, a universe that expands, contracts, and rebounds in a cycle repeating across eternity. In this breathtaking view, the Big Bang was not a unique beginning, but merely the latest turn of the wheel, a moment of rebirth following a previous phase of cosmic contraction. This radical rethinking of time itself completely transforms the narrative of the first elements, because it suggests our universe did not start with a clean slate. Instead, it inherited the chemical remains of a cosmos that lived and died before our own. Within this cyclical framework, the process of nucleosynthesis is no longer a one-time event that occurred in an isolated, newborn universe. It becomes a link in an infinite chain. Picture a previous cycle, a universe much like our own, filled with stars that fused hydrogen and helium into heavier elements in their cores before exploding as supernova, seeding the cosmos with carbon, oxygen, iron, and all the other ingredients for planets and life. As that universe reached its final stages and began the long collapse toward the Big Crunch, all that complex matter would have been gathered together, heated to incredible temperatures, and broken down back into a dense plasma. However, it might not have been broken down completely. Trace amounts of those heavier elements, the ashes of long-dead stars from a forgotten eon, could have survived the contraction and rebound, becoming part of the initial conditions for the nucleosynthesis that occurred in our cycle's first few minutes. This changes everything. The standard model of nucleosynthesis assumes a starting point of only the most fundamental particles, quarks, leptons, and photons. But if our universe was born from the remnants of a previous one, that primordial soup would have been subtly polluted with pre-existing nuclei. These ancient atomic fossils would not have been passive spectators, they would have been active participants. Heavier nuclei from a prior cycle could have acted as catalysts during the frantic nuclear reactions, providing surfaces for new particles to latch onto and opening up entirely new pathways for fusion that are simply impossible in a pure hydrogen and helium environment. They could have absorbed free neutrons, effectively stealing building blocks that would have otherwise gone into forming deuterium and helium, and subtly altering the final chemical yield we observe today. This provides a breathtakingly elegant potential solution to some of the most persistent puzzles. The infamous lithium problem, where the observed amount of lithium-7 is significantly lower than predicted, might not be an error in our nuclear physics. It could be a direct result of this inherited complexity. Perhaps the presence of trace carbon or oxygen nuclei from a previous universe provided a more efficient channel for lithium-7 to be destroyed as it formed, or perhaps it suppressed its production altogether. Similarly, the slight variations we see in deuterium abundance from one ancient gas cloud to another might not be measurement errors, but genuine cosmic fossils, local variations that reflect an uneven distribution of this pre-processed material inherited from the previous cycle. The elemental abundances we measure would then be a palimpsest, a cosmic document where the clean writing of our universe's nucleosynthesis is written over the faint, older script from a universe that came before. The profound implication of the cyclic model is that the first light elements are not truly the first at all. They are the most recent iteration in an infinite series, their specific ratios shaped not just by the physics of the first 3 minutes, but by the entire history of a cosmos that existed before our own. It suggests that the recipe for the universe's chemistry is not written from scratch each time, but is passed down and slightly modified through each cosmic rebirth, potentially explaining why we have the specific, life-allowing mix of elements we observe. It turns the question of our origins from a search for a single beginning into a meditation on an eternal return, where the fingerprints of creation are not from a moment but from a cycle without end. And now we arrive at a theory that stands apart from all the others, one that shifts the focus from how the first elements formed to why we perceive them the way we do. This is the anthropic principal selection, a concept that bridges the gap between hard physics and profound philosophy. It proposes a truly staggering idea. The primordial abundances of hydrogen, helium, and lithium might not be the result of a single, deterministic process, but rather the only possible outcome that could ever lead to creatures like us being here to talk about it. To understand this, we need to step back and look at the cosmic recipe for life as we know it. Our existence depends on a breathtakingly long and delicate chain of events. It requires a universe that lives long enough for stars to form, for those stars to forge heavier elements in their cores, and for those elements to be scattered into space by supernova to eventually form rocky planets and the complex chemistry of biology. Every single link in this chain is exquisitely sensitive to the initial conditions set by Big Bang Nucleosynthesis. Imagine if the universe had produced just a few % more helium. That might not sound like much, but it would have drastically altered the life cycle of the very first stars. They would have burned hotter, faster, and died more quickly, potentially flooding the early cosmos with too much destructive radiation and not enough time for stable planetary systems to coalesce around subsequent generations of stars. Conversely, what if there had been significantly less helium? The first stars might have been less efficient at triggering the supernova explosions that are essential for dispersing life-giving elements like carbon and oxygen across the galaxy. Our solar system and we ourselves are made from this stardust. Without that specific distribution mechanism, the cosmos might have remained a scattered soup of simple hydrogen and helium, never progressing to the complexity required for planets or observers. The amount of deuterium is equally crucial. Too much deuterium would have made the first stars burn their fuel too rapidly, again shortening their lives and altering the entire timeline of galactic chemical evolution. Too little deuterium and certain key nuclear reaction pathways in stars might never have ignited properly. The anthropic principle suggests that we should not be surprised to find ourselves in a universe whose fundamental constants and initial conditions, including the mix of the first light elements, fall within the extremely narrow range that permits our existence. In this view, the lithium problem might not be a problem at all. Perhaps the observed lower abundance of lithium-7 is not a flaw in our models, but a feature of a universe that is bio-friendly. Lithium, while important, can be destructive in large quantities. An overabundance might have complicated the delicate chemical pathways that led to the first self-replicating molecules on early Earth. The fact that our models predict more lithium than we see could simply mean that in the vast multiverse of possibilities where every conceivable value for the constants of nature is realized, we inevitably find ourselves in one of the rare universes where the lithium levels are just right, even if that means they are lower than a purely physics-based calculation would expect. This is not a cop-out or an argument from design. It is a statistical selection effect. If a near-infinite number of universes exist with different physical laws and different elemental abundances, then only in the tiny fraction where those values allow for observers will those questions ever be asked. We are not seeing a finely tuned universe. We are seeing the only type of universe we could possibly see. The light element abundances are then the ultimate cosmic prerequisite. They are the first and most important line on the checklist for a habitable cosmos, and the fact that we are here to measure them is the strongest evidence that they were always going to be exactly what they are. But after exploring 29 different theories, from the turbulence of primordial strings to the silent influence of ghostly neutrinos, we arrive at a final idea that is perhaps the most humbling and expansive of them all. This is the multiverse variations theory, a concept that reframes our entire search for understanding not as a quest for a single answer, but as a realization of our own cosmic address. What if the precise ratios of hydrogen, helium, and lithium we measure are not the inevitable outcome of a fixed set of physical laws? What if they are simply the local bylaws of our particular universe, one tiny island in an infinite archipelago of realities, each with its own unique and randomly selected set of rules? This idea springs from a profound observation in modern theoretical physics. Many of the fundamental constants that govern our universe appear to be finely tuned for the existence of complex life. The strength of the strong nuclear force, the mass of the electron, the initial amount of entropy, if any of these values were even slightly different, the universe as we know it would be impossible. Stars wouldn't form, atoms wouldn't hold together, and the cosmic tapestry would be a boring, lifeless blank. The traditional response to this fine-tuning has been to search for a deeper physical reason, a theory of everything that would explain why the constants must have the values they do. The multiverse hypothesis offers a radically different, almost Copernican explanation. There is no deeper reason. The constants are random, but in a truly infinite multiverse, every possible combination of physical laws and initial conditions is realized somewhere. We naturally find ourselves in one of the rare universes where the numbers are just right for our existence, not because it was designed for us, but because we are a product of its specific, life-allowing parameters. Apply this breathtaking concept to the puzzle of the first light elements. In our universe, the proton-to-neutron ratio, the expansion rate, and the nuclear reaction cross-sections all conspired to produce roughly 75% hydrogen, 25% helium, and a tiny trace of lithium. This specific mix was crucial. It allowed for the formation of first-generation stars that were stable and long-lived enough to forge the heavier elements and eventually seed the cosmos with the building blocks of planets and life. But according to the multiverse theory, this was not a guaranteed outcome. It was a cosmic lottery ticket. In the vast majority of other universes, the dials were set differently. Imagine a universe where the strong nuclear force was a fraction of a percent weaker. In that reality, deuterium, the crucial stepping stone to helium, would be so unstable that it could never form. The nuclear chain reaction would stall at the first step, leaving a universe filled with nothing but lonely protons, a vast eternal sea of hydrogen with no stars ever igniting to break the darkness. Now picture the opposite, a universe where the nuclear force was slightly stronger. In this reality, deuterium would form too easily and fuse into helium with frantic efficiency. The primordial nucleosynthesis would have been too successful, cooking nearly all the available hydrogen fuel into helium and heavier elements right from the start. Without a large reservoir of hydrogen, future stars would have had nothing to burn, and the universe would have aged into a cold, dark graveyard of helium-rich corpses almost immediately after its birth. Our universe, with its specific light element abundances, sits in a breathtakingly narrow Goldilocks zone between these two sterile extremes. We have just enough deuterium to jump-start the formation of helium and future stars, but not so much that it burns out of control. We have just enough helium to enable efficient star formation and metal production, but not so much that it stifles the universe's potential from the outset. The lithium discrepancy itself might be a key part of this fine-tuning. Perhaps a higher primordial lithium abundance would have somehow poisoned the well for later organic chemistry, or altered the internal workings of the first stars in a detrimental way. In the multiverse view, our universe's specific elemental recipe isn't a problem to be solved. It's a prerequisite for our existence. We shouldn't be surprised that our measurements don't perfectly match a model that doesn't account for this selection effect. The model calculates what would happen on average across all universes. We live in a very special, non-average universe, one that is bio-friendly. This is the ultimate cosmic perspective. It suggests that the 30 theories we've explored are not necessarily competing alternatives. Instead, they could all be simultaneously true, just not here. In the infinite multiverse, there are universes where primordial black holes disrupted nucleosynthesis, where variable constants altered the nuclear cross-sections, and where a dominant sea of tau neutrinos skewed the proton-neutron balance. Every possible physical scenario is realized in some cosmic corner. Our quest to understand our own origin story then becomes a process of not just discovering the laws of physics, but of mapping the contours of the wider multiversal landscape to understand why our particular neighborhood is so perfectly suited for life. The first light elements are more than just ancient relics. They are our universe's identification card, a chemical fingerprint that marks us as one of the rare, habitable worlds in a vast and mostly inhospitable metacosmos. And so we reach the end of our cosmic journey, a voyage that has taken us from the perfectly smooth predictions of the Standard Model through 30 wildly different and extraordinarily creative theories. We've imagined a universe born from a collision of brains, sculpted by the whispers of ghostly neutrinos and seasoned with the ashes of a previous cosmic cycle. We've dared to question the constancy of the speed of light, the very fabric of gravity, and the number of dimensions that make up reality itself. Each of these theories, from the well-established to the highly speculative, is far more than just a set of equations. It is a profound testament to humanity's boundless curiosity and our relentless, awe-inspiring quest to understand where we came from. This incredible diversity of thought isn't a sign of scientific failure. It is science in its most vibrant and alive state. It represents the courageous act of staring into the deepest mysteries of existence and refusing to look away, even when the answers don't come easily. Every time a new telescope provides a more precise measurement of an ancient gas cloud, or a particle collider recreates a fraction of a second of the early universe, it's like finding a new piece of a cosmic jigsaw puzzle that's 13.8 billion years old. Some pieces fit neatly into the established picture, while others force us to consider that maybe we've been holding the box lid upside down all along. The fact that we are still debating the first 3 minutes of everything is a beautiful reminder that the universe is under no obligation to be simple, and that the greatest adventures in discovery are still ahead of us. And this is where the story truly becomes yours. I want you to consider which of these theories resonates most deeply with you. Does the elegance of supersymmetry and its shadow particles appeal to your sense of cosmic balance? Or does the monumental drama of a cyclic universe, endlessly reborn from its own ashes, feel more compelling? Perhaps you're drawn to the subtle, ghostly influence of the cosmic neutrino background, or the mind-bending possibility that our reality is a holographic projection from the edge of space. There are no wrong answers here, only an invitation to marvel at the fact that we can even ask these questions. These primordial elements, hydrogen, helium, and that tiny, stubborn trace of lithium, are so much more than just the first entries on the periodic table. They are the universe's first words, the opening sentence of the greatest story ever told. They are the raw material of stars, the fuel of galaxies, and the very atoms that make up most of your body. Their origin is our origin, and that is why they continue to captivate scientists and space enthusiasts alike. They represent the ultimate cold case, a forensic investigation into the very moment of creation. Every new theory is a new lead, a fresh perspective that brings us one step closer to understanding our place in this vast, astonishing, and wonderfully mysterious cosmos. The conversation is far from over, and your curiosity is the most important part of it. But of course, the most thrilling part of this conversation is that it doesn't end with this video. It continues with you. I'm genuinely fascinated to know which of these 30 theories captured your imagination the most. Did the mind-bending geometry of extra dimensions resonate with you, or was it the silent, ghostly influence of the cosmic neutrino sea? Perhaps the dramatic vision of a cyclic universe, endlessly reborn, felt the most compelling. Share your favorite in the comments below. I read every single one, and there's nothing I love more than diving into these cosmic mysteries together with this community. If this is the kind of deep dive that fuels your curiosity, then you're definitely in the right place. Make sure to hit that subscribe button and ring the bell so you don't miss our next journey to the edge of discovery, where we'll continue to unravel the universe's greatest puzzles, from the nature of dark matter to the search for life beyond Earth. As we close, I want to leave you with a final thought that ties all of this back to us. We've spent this time exploring the universe's first chapter, the creation of hydrogen, helium, and lithium. But these aren't just abstract concepts in a physics textbook. That hydrogen is the fuel of every star that has ever shone. That helium is a product of those stars' furious nuclear furnaces. And those elements are the very reason we exist. Every atom in your body was forged in the heart of a long-dead star, but the raw ingredients for those stars came from that primordial forge in the first 3 minutes. We are quite literally the universe becoming conscious of itself, looking back across 13.8 billion years and asking, how did I get here? This quest to understand the first light elements is so much more than a technical challenge. It is a fundamental part of the human story, a continuous thread that connects our most ancient ancestors gazing up at the night sky in wonder to the scientists of today peering into the data of mighty telescopes and powerful colliders. It is a journey of curiosity, perseverance, and awe. We are all part of this grand, ongoing effort to read the cosmic recipe book, to decode the faint chemical whispers from the dawn of time, and in doing so, to better understand our own extraordinary place in this vast and magnificent cosmos. The search continues, and the next great discovery could be just one observation away.